Are you gonna put a bonus word for Dwight?
Oh yeah, I should. Is he not here? That was funny. Yeah, did he ever actually realize that? I didn't think so. All right. So like last time, let's just start off with the general equation for photosynthesis. And I'm going to put in a different color than black, the stuff that we're actually going to be dealing with today. So today we do see the CO2 come into play. We are not going to be working with water. We're also not working with that light energy today. We are going to be showing that sugar forming. I'm saying sugar instead of glucose because it's not always glucose. And we will not be dealing with oxygen today either. So, main goal of today is getting carbon dioxide to sugar. That's what we're doing. Everything else we've already done in the light reactions. So we've already split apart that water to generate the ATP and NADPH needed using that light energy. So now it's time to cash in that energy. So let's go over here. All right, there are three major stages to the Calvin cycle. Do this here. We're going to have a carbon fixation stage. Carbon fixation just means to take environmental sources of carbon and convert them into biological sources of carbon. You are fixing the carbon into a molecule that can be used by an organism. Okay. And that's going to be our very first stage. Then there's going to be a reduction stage, and then there's going to be a stage where we regenerate the starting material for the Calvin cycle. So we need to start with carbon fixation. And the source of carbon that we are going to be fixing is CO2. Okay, so we'll do what we did yesterday. We'll write out what happens and then we'll add it to the diagram. Just keep going like that. So what we see here is atmospheric. Oh, are you working off the wrong diagram?
No, I just got ink all over it.
Oh no. Okay.
I think yeah.
I don't know what happened with some of my printouts here. It's like I printed the wrong thing on some of these. No, there's one. There's one.
Okay. Here we go. So, atmospheric CO2 is attached to, this is a carbon-based molecule called RuBP. Okay, Rub. And this is done by an enzyme called Rubisco. I'm not sure. I hope it's not. I hope someone just actually named it Rubisco. We'll have to look, I'll look into that. I'm not sure. It kind of does. So what this is going to do is it forms an unstable intermediate. So forms an unstable 6-carbon intermediate. An intermediate is just something that is formed in between where you're actually headed. So this is just a very short-lived molecule And it is going to then split into 3 carbon molecules. So that's going to be stage 1. Atmospheric carbon dioxide is going to come in through the stomata of the leaves, which are those tiny little openings that the leaves can open and close, or plants can open and close. Atmospheric CO2 comes in, and then it's going to be attached to this small sugar molecule, RUBP, which is the starting and ending product within the carbon cycle. That fixes the carbon. Okay. So, are we good there? To the diagram. So this is happening here. So we start off with carbon dioxide coming in. And then I'm just going to outline the arrows in the color where it pertains to what we're talking about. Here's that Rubisco, it's an enzyme. Okay. So CO2 comes in, we form that short-lived intermediate, and then it's going to break down into this 3-phosphoglycerate, which you don't need to know all of these terms. We just need to know the overall processes, the inputs and the outputs. Okay. So that is the end of the carbon fixation stage. So next then we are going to go into our reduction stage. This is number 2. Reduction, so if we are about to reduce this thing, we're going to have to, are we taking away electrons or are we delivering electrons if we reduce it? We're delivering electrons. Where are those electrons going to come from? Yeah, so the NADPH that we formed in light reactions. Exactly. Okay, so in the reduction stage, we see ATP and NADPH produced in light reactions. Provide the energy, which comes from the ATP, and free electrons, which comes from the NADPH. To form the sugar G3P. Okay, so G3P is not a biologically significant sugar. Like, we don't directly use it for anything, but it's a really important intermediate that gets us to all the sugars that we do use. So from this step, let's add a bullet point here. Some of that G3P is going to remain, some of it's going to move on through the cycle. So one of the G3Ps that's produced is going to be used to construct biologically significant sugars. So I'm just going to say bio-sig, because we've used that word a bunch now. Biologically significant sugars, comma, while the others move on to regenerate the RUBP. So this is what makes it a cycle. We're not using up all of the RUBP, because if we did, it'd be like a one-way elevator. This whole process has to be reset. So to reset this process, we're only using a little bit of the G3P at a time, and most of it's going back into the system to regenerate the RUBP. Okay, so let's show where this is happening. We move on over here. So we have our 3 phosphoglycerate molecules here, and we're going to see ATP coming in. This is going to provide some energy to some enzymes that do some stuff that we don't care about. Okay. And that gets us to the 1,3-biphosphoglycerate, which again, you don't need to know that. But what do you notice is different between the two? Look at this two. Actually, phosphate group, where'd it come from? ATP. So we just phosphorylated the phosphoglycerate. So, we'll outline that one in this color. Hello. Thank you. And then we are going to use our NADPH to reduce this thing then. So NADPH comes in, and NADP plus is going to leave. Technically, some water gets released here too, but for whatever reason that's never shown in the equation, so we're just going to leave that. We're going to slowly back away into the shrubs like we didn't see it. Because it's not mentioned in your book, so in case for whatever reason you see it on the AP exam, technically on this step right here, there's some water released. So that takes care of our reduction stage. Oh no, that's almost. So then we have our G3P that's produced right here. One of those G3P molecules is going to be set aside here to start building some sugars, some other sugars. But most of them are going to move on in the cycle towards the regeneration stage. Okay, so here is our G3P. It is a sugar. It is a 3-carbon sugar. And we would use multiple G3Ps to start building. So used to synthesize biosig sugars, such as glucose or sucrose, or maybe you want some fructose, or maybe you want some maltose, or some of the other doses. So, Calvin cycle doesn't directly produce glucose for any of those other sugars, but it produces the thing that will then be stuck together to make all of these other biologically significant sugars. Great. So now we move on to the last stage, which is going to be getting back to the RUBP. Third step. RUBP regeneration. And that's what makes this a cycle. We are ending with the same substance that we started with. So ATP is used to power a series of reactions, frictions, which converts G3P into RUBP, resetting the cycle. So, not quite as much going on as with the light reactions. there. Okay, we move back to our diagram here. What you'll notice is a couple things. So what we're doing is we're taking these G3Ps, which only have 3 carbons, and we're going to produce fewer molecules, which are the RUBPs, that have 5 carbons. So that means we're sticking some of these things together. Right? That's going to make a chain, and then chop them up to make our RUBPs. That's what those enzymes will be doing. This is the section of the diagram, so we go ahead and fill in our arrows right here. The ATP would come in right here and leaves as a DP plus a P. I forgot to put what this thing is actually called. This is the Calvin cycle. And it occurs in the stroma. Also, what else is different between the G3P and the RUBP? It has an extra phosphate group, which came from the ATP. Phosphorylation happened here as well. All right, let's add a couple last things on the bottom here. Okay, so first of all, where does some of this stuff go? Well, yeah, I'm just going to do this part in bulk. The ADP, the extra phosphorus, and the NADP plus are going to be recycled back into the light-dependent reactions. The other thing is that the sugars that are generated, so the sugars generated by the Calvin cycle are going to be used by organisms in cellular respiration to make ATP. And that's how these things are so well connected. So not only are the equations for them indicative of how cellular respiration's products form the reactants for photosynthesis and vice versa, but photosynthesis generates the sugars, cellular respiration consumes the sugars, and then replaces all of the raw materials needed for photosynthesis to happen again. These two processes work perfectly together, and they clearly more evolved at the same time. Okay. So, I think, we just got to fill in our top little structure here again. I just want both of them to be like together. So here in the light reactions, we had water coming in with light energy. This happened in the thylakoid. And we generated some oxygen and some NADPH and some ATP. And then that was used to power the Calvin cycle, where we saw CO2 coming in. We were generating G3P, which then went to biosig, sugars. This happens in the stroma. And we are going to send AD, P, and P. And NAD, P plus back into the lab reactions where the whole process will start over again. All right, I think that's it. Questions? Is that good?